Hello everyone, I'm Simon Danisch. I will present Julia today, which I consider the compiler for the future. If I'm a bit nosy or a bit unenthusiastic today, it's because I just got sick before the talk. Sorry about that. Well, I study cognitive science, which is not 100% related to do what I do nowadays, but it got me interested in computer vision and machine learning. And I got very interested in language design to do computer vision and machine learning in a better way. And that's how I ended up working for the Julia lab and developed a couple of packages for GPU computing and graphics on the GPU. And now I work at Next Journal as the Julia expert, basically. This is also the whole talk is written in Next Journal. I will publish the article after the talk so you can see it online, follow the links and further materials that I will present in the talk. So this also has a slideshow mode. Yes. The motivation for this talk is at Next Journal we have very high interest in interactive workflows for data science, interactive computing. I share these interests for low-level computing, like how to write libraries that are really fast and still are nice and interactive to use. And I'm really interested in extensible machine learning frameworks where you can just get started and hack around on them and they're still being fast. And that's how I got to the Julia language, and I want to share with you what I like about the Julia language and how it compares to other languages. And if you're interested, I have this broad statement, the compiler for the future. I think you really should look at the present and the past to figure out how the future should look like. And if you do that, if you look at the languages of the present and past, you will see there's this one really successful language, Python, especially for machine learning and data science. It's skyrocketing right now, so I think we should really try to understand what makes Python successful. Yes? Oh yeah, thank you. Yes. So what is Python? It's an interpreted and dynamic multi-paradigm language, meaning you can write it in a more functional or more in an object-oriented style. It's really convenient if you write lots of script interactively and just redefine functions and execute them while you go. It's kind of slow because it's interpreted, so it can be 50 to 300 times slower than pure C. It has a very simple and appealing type system for the users, and it has some basic metaprogramming, which seems to work very well for a lot of people. And because it's so successful, you could assume people don't really care about performance. But since it's used for data science and machine learning is one of the main factors that it's growing so much, like I think one of the most successful libraries are TensorFlow, PyTorch, Keras, and Theano. You mainly use them from Python, so that's a big factor behind the growth. And if you look at further statistics, this blue line is pandas, NumPy, and matplotlib, some very famous packages for data processing and data science, and they're also skyrocketing, which is really odd, because if you know data science and machine learning, you know that it has a high need for performance because some tasks may take a couple of days, even if it's fully optimized, and if it's 300 times slower, that means it takes a couple of years. But still, Python is the most popular language for it. This is just weird. But there's a simple explanation for it. So most of these packages at their core are actually written in C and C++. And what this shows is that Python is a really great language to fuse and glue these packages together that are actually written in another language. And if you look at the most successful packages in Python, and if you look at NumPy and pandas, you will see that they are actually written at their core in C++. So they can actually offer very fast performance to their users, even though they interact with them in Python. So this really gives us the best of two worlds in Python. You get the number crunching and fast compiled libraries, while the user in front of it can interact with them in a fun and dynamic language without any compilation overhead. But from the title of my talk, you can suspect that I have my doubts with this. So those Python packages that are written in C++ at their core, they usually don't work with user custom types, or they will be very slow because C++ has to analyze them what kind of objects they actually are. Or if you give to the state-of-the-art C++ solver, if you give them a Python callback, this callback will be called a lot of times, and it will slow down the whole thing, even if the C++ is state-of-the-art. You can't optimize your whole program because you kind of have a wall between Python and C++ because they don't work in the same compiler. You can't just have one compiler pass going over Python and C++. And whenever you have a popular pure Python package where people hit performance boundaries, they will need to start to rewrite it in a different language, which is, of course, costs money and is a lot of work. And you get into the two-language problem where your package is really hard to maintain and it's hard to contribute. So if you get a bug in a library and suddenly see the stack traces point to a C++ library, at least for my case, that's really demotivating. And because C++ is just that much harder to set up and get into. And of course, a lot of Python people probably don't even know how to write C++. So what can we take away from this? In the Python world, it seems like people trade an interactivity and development speed for getting slow execution times and no real static typing. Static typing, probably a lot of people in this room love this for having more stable software. And what we also take away that most of the core libraries are not actually written in Python, which is really sad, right? You have this language everyone loves, and then in the end, the packages are not written in that language. So here, I really want to figure out how a language would need to look like to actually write also the core of the performance bound of the package in the same language. And I think for that, we first need to really understand how those packages and libraries for machine learning look like, to see what their demands are for the language. And this is a very high-level view on most machine learning of the process that happens inside neural networks, for example. So you have this tunable function here. You give it some input, and it gives some output. And in the beginning, you start with random with an untuned function, so it gives you basically random output. Then you train it a lot. This may take a couple of days even, or a couple of hours. And after that, you hopefully have a fully tuned function that gives you reasonable output for the input. And for example, classifies this picture of a butterfly correctly. And how does this tunable function look like? It's usually made up of multiple layers. In each of those layers, you're calling multiple functions. They are usually like convolutions or other tunable functions with weights. So you have these weights, and the training process updates these weights to change the function in the way that it actually does the predictions correctly. And how does this tuning work? It uses the algorithm backpropagation usually. I made a very small example for this. So this is our tunable function, which is the most simple one I could think of. It's basically just a chain where at each joint you have an angle, which is the weight, and via tuning the angle you can have the chain reach a certain point. So when I do this here, you can try to reach this point. And the loss function, which is usually used to see how far you're away from a target, in this case is just the distance to this red point, which is our target. And what backpropagation does is it takes the gradient of that loss function towards the weights so that we can update the weights to push our function in the right direction. And if we run this, we can see it correctly tuned our chain to reach this point. And most machine learning models work in this way, although the layers will be much more complicated than that. And they will have millions or maybe even, millions of weights. So it's computationally very heavy. And what do we take away from this? So these neural networks are built from many small parameterized functions. The loss functions will need to call through all those layers and actually need to call those functions. And the functions could be any user-defined function, or depending on the machine learning frameworks, they have to be primitives from the machine learning framework and they can't be user-defined. And the reason for that is that frameworks need to differentiate the loss functions to get the gradient. And this needs to execute really fast because it needs to churn through a lot of data. And if you don't have automatic differentiations for those functions, you can only rely on the predefined functions from the machine learning framework. So what's automatic differentiation? I can't get too deeply into this, but a very simple example here. So you have a user-defined function here, our example function, which does just very simple things. And that could be like our automatic way of deriving it. Here we just do it per hand. But if we want to do it automatically, a compiler or a framework would need to do this transformation from replacing sine and cosine and putting a minus there. It would need to do this automatically. And since those layers are very big, a huge call graph needs to be transformed like that. And as I already said, the result must have flawless performance. So we actually need to do compiler optimizations on the results, like fusing calculations. You might want to inline resulting functions. You want to remove temporaries. And finally, usually you want to execute the result on the GPU. And this is very deep in the territory of compiler and language research, because that's exactly what most compilers do. And this is not only my idea or the idea of the Julia people. A lot of big companies and frameworks start recognizing this, and they create more and more intermediate representations, which are small, low-level languages where they do these transformations inside and do the automatic differentiation. So just to name a few examples, Facebook with PyTorch created the PyTorch IR. Google created a whole range of them, like XLR, machine learning AR, and JAX. And what they do is, if you have your Python framework, they either from the API call, they trace through the API calls, or they directly translate the source to their own intermediate representation, and that's where they do the automatic differentiation and all the compiler optimizations. And then they use, for example, LVM, an extensible compiler framework, to generate native code from that, which then is very fast to execute. Now, what if you're not Google or Facebook and can't actually just go out there, hire a huge team, and create a new language to do your optimization inside? And I think that's where Julia comes into play, because Julia offers a lot of these things for free. What is Julia? It's also a multi-paradigm language. So you can program it in a functional style or more in an object-oriented-like way. It's also very dynamic, so you can redefine functions, you can evaluate code, but it's compiled at runtime, much like C, so you also get C-like performance. I think it's on eye level with the ease of use with Python, so you can just very quickly get started with it, write a little script, and get your math in place, because it's also optimized, the syntax is optimized for writing math. And what's, I think, really outstanding is that the compiler is very transparent, it's very easy to get into it, and there are even things like compiler plugins. And since you have a JIT already, a just-in-time compiler with the language, you can just generate new code on the fly. It comes from Lisp, so code is basically data. You can interact with it like any other data structure, eval it, get new functions. And the compiler is, and the runtime is available through all stages. So just show you how this looks like. This is a macro in Julia, which does a very simple transformation. So it gets in an expression, which is this println here. So that's the input of this macro. I show how it looks inside here in an S form. So you just have the head, which is a call, and then the function and the hello as an argument. And I can just transform it, for example, add an argument to this function call, so that after it has the second string in here, and then if we execute it, it will actually say println hello world. And Julia has a lot of reflections for all functions, so if you have any user-defined functions, you can get all compiler stages of that and interact with them. So if we go back to our example functions, you can get the lowered form as a data structure from the function, which is here Julia's AR, intermediate representation. And you can get the typed version, which has all variables with inferred types. And you can even get the LVM intermediate representation and the native code that is generated by it, which is very handy if you really want to fine-tune things or actually work with the intermediate representation. And just to prove my point, this is I don't want to explain this code, it's just a bit too complicated to dive into it, but it just shows how you could easily go through this data structure, replace some functions, and generate a new body for that function, and then eval it. And what I do here is I just replace cosine and sin, add a minus in front of the sin, and then eval a new function here, which is pretty much what we would need to do the automatic differentiation. And if we check this new function, it does actually do what we want it to do. And if we look at the LVM code, we can also see that it generates nicely inline code, and it looks pretty optimal. Yes. There's also a library for that, where you can write these kind of compiler passes. It has a very simple API where you can just say, instead of calling this function, call this other function with the same arguments. And then in this function, you could also get access to the intermediate representation of that function, so you could transform that function into a new form. Here, I just use it without accessing the intermediate representation. I basically just do what I did before. I just replace cos and cosine. And we can see if I execute this function in this new context here, I will also get the derivative. And that's actually how the state-of-the-art automatic differentiation packages in Julia are written, pretty much. And they work with user-defined functions, they work with user-defined types, and generate efficient code that can run on the GPU. So that's why I think that Julia is uniquely fit for those machine learning challenges, because it has this just-in-time compiler, and also because it has state-of-the-art GPU support, where you can just take almost arbitrary Julia functions. Of course, since it's a different hardware, there are some things that just don't work, like the GC. But it works with user-defined function and types. So it's very easy to then put the loss function on the GPU. And that was a lot of talk, but there's also somewhat a proof that this works out. So there's this Flux machine learning library, which is purely written in Julia. It's pretty much written by one person, although in the last half year, probably more open source contributors got into it. But that also proves my point that it was very easy to actually start working on it for them. And this one person managed to basically pull off to get on eye level in terms of functionality and performance with TensorFlow. And you don't have this two-language problem with this framework. I can only recommend to look into this framework because it's pretty impressive. And what this awesome automatic differentiation support in Julia also means is that you can bring your own packages inside these layers. So you can use packages that are not written with machine learning in mind. And I have a few examples here, but I think I'm running out of time, so I can't fully show them. But when I publish it, you can look at them. So, for example, there's an example where they go through a whole physics library, and because they can differentiate it through it, they don't need to have a lot of training data. And there's differential equations, which also works with Flux out of the box, even though they weren't created for each other, which is pretty impressive. That's the physics library. So they have this throwing thing to hit a target. And if you look at the work that is needed, if you actually need to rewrite, if you can't bring your own packages, so you would actually need to write a whole physics library in TensorFlow primitives, or you would need to write custom custom differentials for your kernels, and then you can just start by writing your actual neural network. And maybe at that point you figure out that your idea wasn't very good and you wasted a lot of time. So if you can already use existing packages, this is shortened quite a lot. And I think this whole talk makes a point about that it's a language problem, machine learning, and that the language needs to be tailored for it. So why don't I make the point that we need a machine learning language that is specific to machine learning? And I think that's because you need a lot of general purpose around machine learning, like data scrubbing, preparing the data, maybe have a UI around it, or dashboards. Or maybe you even want to apply general purpose algorithms inside the neural networks. And I think that's why I would stick with Julia for that, even though it might not be as tailored to it. So as a summary, I think the good parts are Julia is really great at writing and getting into the compiler. The code pretty much has optimal performance because at runtime it's generated much like C. It solves the two-language problem, and it actually has a pretty nice type system. I didn't really have time to get into this, but if you're interested in Julia, you should really look at it. I think the type system is actually explained in another talk, so you should have a look at that. And it loads the interactive workflows we love from Python. The bad, what I need to mention is, well, we are compiling stuff much like C, so we also have compilation times like C, which can be very annoying in an interactive workflow. The good part is, once you start Julia, once it started compiling, you also only need to compile the differences, which are usually very small and fast. But yeah, you need to wait more than in Python for that. But I think we have very exciting solutions for this, and that brings me to my first thesis where I said Python and C++ are a great mixture in Julia, we could actually have something very similar by having parts interpreted in Julia and parts statically ahead of time compiled, which is already possible, but it's a bit complicated to do this. So we have an interpreter in Julia, we have an ahead of time compiler for Julia, but they're still a bit immature. But in the future, I think this will work out great. And you have the Lisp in there. So Julia comes from Lisp, basically. The creator was a big fan of Lisp, and that's why you have a lot of these code transformations and meta-programming in there, which makes it great for example, for automatic differentiation. Thank you very much. Any questions?
Thanks for the talk. Small question, how advanced is the LLVM support? So can I use it as a foreign function interface? For instance, compile something down to LLVM from C and JIT it or load it in Julia? Is that possible?
Is the foreign function interface for C?
So I mean, can I use the LLVM part in Julia as a foreign function interface? Can I compile from C to LLVM and load it in Julia? Or how advanced is it support for LLVM in Julia?
Sorry, I can't hear it very well.
Okay, again. If I compile something to LLVM bitcode from, like, let's say C,
yeah,
can I load it as a bitcode in Julia?
Yes, it's a bit complicated, but there's actually a package for that, which just recently got renewed. It's called cxx.jl, and it pretty much does that. So it takes the Julia compiler with LVM, and then it uses Clang to parse C and transforms it to the LVM IR, and then on that level they fuse it. And it actually, in that framework, it's possible to inline C++ function inside of Julia program. So then you can even do whole program optimizations between Julia and C++ if you do that.
You had all these marvelous examples ready to show. We have a few minutes left. Could you show us some of them?
Good point. Well, oops. Well, that's awkward. Am I disconnected from the internet? No. Nothing a simple refresh can't fix. So this is a whole article about two students using Flux with a physics library together. And what they want to do is they want to aim this, what's it called? Trebuchet at a certain location. And they use a Julia physics library and Julia's automatic differentiation tools to actually differentiate through the whole physics library, how it calculates where the ball lands. And then if you take the gradients from that, you can actually figure out how to aim the trebuchet, because you know in which direction to tune it, which is very similar to the Shane example I showed. But of course, the physics behind it is a bit more complicated. Yeah, it's a whole article. I don't think I can show the whole thing. The other one, I'm not a big expert in differential equations, but everyone who knows differential equation, and I know, is super excited about this, because you can actually, in your neural network layers, you can use differential equations to solve something, and the automatic differentiation can just go through it, so the optimizer can do its job on those layers and actually learn on it. I think there has been a very interesting blog post I should probably also include in the article. What do they do? It's a lot of code. Yeah, this is not really my expertise, but I hope anyone who's interested in differential equations could be interested in this. Yes.
Yeah. How do you go about compiling Julia programs to the GPU? Because it has like a runtime and a garbage collector.
Yeah, so the question is, how does it work to compile Julia to the GPU? And what we do is we take the LVM intermediate representation of static subgraphs of the Julia language. So it only works where the type inference worked completely, although the newest version is a bit more permissive because they implemented a small GC on the GPU. Yeah, it's pretty exciting. But yeah, and from this static subgraph, they use the LVM GPU backend to compile for NVIDIA GPUs right now. And it's on par with the performance of any C kernel. I think you don't have access to absolutely all low-level constructs, but I think that's just yeah, you just need to wrap it basically. But I think it's 95% of the APIs are exposed. Yeah, and I wrote a transpiler for Opencl, which was a lot simpler, and I basically just did I just got the source code for the functions, cleaned it up a bit, and created a Opencl string, which I compiled with Opencl, which worked pretty nicely, but I ran out of time when they upgraded to Julia 1.0, where the whole intermediate representation changed, so it's not working at the moment. So it's just NVIDIA right now. But there's a very exciting project which slowly comes to fruition where it's working with AMD's CUDA counterpart ROCm, and that works exactly the same way the CUDA framework works. So no ugly transpilation or stuff like that. I hope to see that at JuliaCon next week, actually.
How stable is Julia as a language? You said you have, or it doesn't work after the update to 1.7. Will there be a 1.0, sorry. Will there be a 2.0 in the future and you have to rewrite everything again, or how stable is it now?
In general, or my transpiler? That's a good question. So from what I've seen in the milestones, it looks fairly okay at the moment. So just minor upgrades for APIs. I think the core API is supposed to be very stable, and they will just try to stick to upgrades. Although the intermediate representation might change a lot. But I think the creators of the language themselves are not fully aware what 2.0 will bring, because I think the timeline is something like in 5 years for 2.0 or 3, I don't know. Cool. Thank you.